Hello class, welcome back to Introduction to Material Science Engineering. This is chapter 5 in the Callister text, and we're going to be speaking today about imperfections, especially in crystalline materials. These are very important for having materials move and for diffusing or migrating species from one part of a crystalline material to the other. So this lecture follows on from our discussion about chemical bonding, especially about equilibrium low energy positions of two atoms or two ions relative to one another. This was in our chemical bonding in chapter 2 of the Callister text, where we calculated bond energy, potential energies, and the energy well as a function of interatomic spacing. And then we'll also be drawing quite a bit from our discussion of crystallography in chapter 3. And we'll be using that to discuss imperfections in crystals. So 3 ways that we classify imperfections in crystals, and it goes by dimension, meaning spatial dimension. So we have 0D, which are effectively point defects. There's 3 types: vacancies, self-interstitials, or interstitials of one type of atom in what's effectively a lattice of another, or substitutional atoms, where you have one type of atom instead of another on a lattice point. We have one-dimensional defects or line defects, which go by the name of dislocations, very important for deformation and processing. Then we have 2D defects, planar defects, or surfaces within a material microstructure, also known as area defects. And the most important of these are grain boundaries, although there are 2 other types that we will discuss a little bit. Okay, so we're going to start with 0D and work our way up. So the simplest type of defect or point defect that we can envision in a material is a point defect in a metal. So you can see that this is an image taken from the Callister text. So if you're reading your text, this will be somewhat familiar. So we're looking down on a plane of atoms in a metal, and at one lattice position, say maybe a corner on your unit cell, we're simply missing an atom. It's not there. This is known as a vacancy. So if you think about the potential energy of all of the surrounding atoms in terms of your potential energy versus interatomic spacing diagram, where your energy hits a minimum when those atoms are at their equilibrium spacing relative to one another, which you may have calculated in an exercise, depending on your course structure here. They want to sit at a given position relative to one another, a different spacing. And because we have a vacancy, at least the 4 or 6 atoms around that vacancy are not in their equilibrium position. If you're not in your equilibrium position, you are at a higher energy, and therefore the crystal is at a higher energy. The more vacancies you have, the more atoms in that crystal that are not at their equilibrium position, the more atoms at a higher energy, the whole crystal is at a higher energy. It's less stable. And this higher energy as a result of not being in the right position relative to that equilibrium spacing is also known as strain energy, and it is a type of mechanical elastic energy. And we can use that to drive processes, actually. And there is no surprise that that is also related to elastic modulus, which is one of those properties you may have remembered from our chemical bonding section that is related to the depth of the potential energy well. So we're drawing on that same concept: not in the right position, elastic strain, higher energy. Self-interstitials. It's basically the flip side. You can be missing an atom, or you can actually have an extra atom. These are more rare because typically a self-interstitial, an atom is really too big to fit into most interstitial positions within its own lattice. It's much more likely that you would get an interstitial solute of a smaller type of atom dissolved in another type, or obviously cations in an anion lattice. But the type of energy increase in the crystal is going to be analogous to a vacancy. The surrounding atoms are moved off of their equilibrium position, therefore their potential energy is higher. You've introduced elastic strain into the lattice in 3 dimensions all around that self-interstitial, and the addition of energy to the crystal is proportional to the number you've got. Speaking of the number you've got, that depends on temperature, especially for vacancies. This is the equation for the equilibrium concentration of vacancies in a material, and you can see it depends on a couple of things. The first is activation energy. That's shown in sort of the brownish red variable with a labeled term, Q sub V. Q is a term that's used for activation energy for many different processes. If you've taken some chemistry classes, you may have run across that. And the subscript V just refers to vacancy in this case. We will be looking at activation energies for a lot of other processes, especially diffusion, which, in point of fact, relates to this. So stay tuned. Temperature is in the denominator in the exponential term, but because you have a negative sign within the exponential term, higher activation energies will lead to fewer defects per unit volume, and higher temperatures will lead to more. So just remember you have a negative sign there. This is typically expressed in number of defects per number of potential defect sites. The black n in the denominator on the left-hand side of the equation, and obviously the number of potential defect sites is just the total number of atoms on any lattice position. And so these are usually actually expressed in terms of volume. So typically that black n will be moved over to the right-hand side and expressed as a number of atoms per unit volume. And so obviously you can get that by relating density and atomic weight. And so you would end up with a number of defects per unit volume of the material. And then our green term over in the exponential term is just Boltzmann's constant in energy per number of atoms per unit temperature. And so obviously the units in the exponential term should all cancel out, and that will be a dimensionless term. So important trends: higher activation energy means fewer defects at any given temperature. Higher temperature means more defects for any given material. So in addition to having vacancies in a pure material or having a self-interstitial in a pure material, we can start now mixing different elements, different materials within one another. And this will give us a solid solution. You're probably really familiar with other types of solutions in liquids and gases because we encounter them all the time in everyday life. In fact, you're breathing a gaseous solution now, air being composed of nitrogen and oxygen in a solution. Salt water, sugar and water are very typical liquid solutions. You don't have multiple different phases in those cases. It's all one phase, dissolved, basically all words denoting solubility. Something different would be, say, milk or cream, where you actually have the casein protein and the fatty acids forming their own phases, and that's one of the reasons that those materials are opaque, because light can scatter off the multiple phases. So just like salt water in the ocean being a liquid solution of sodium chloride in water, we can get solid solutions at any combination of temperature or pressure of especially different metals in one another. So it's all a solid phase, but it is a solution of one in the other. So there's 2 types of those. One, substitutional, where you have a solvent metal, the majority number of atoms per unit volume on lattice positions, and then every so many crystalline lattice positions, say a corner atom in an FCC or a face atom or a center in a BCC, you'll swap with a different type of atom. And the most common example of this is copper nickel, which are completely soluble in one another. So you can take any nickel in its lattice and swap it with a copper. Interstitials form when you have a big size difference between your solvent, your lattice occupying material, and the solute. So the the most common example there is iron and carbon, where you would have iron on the lattice positions, and then the much, much, much smaller carbon atoms would occupy the interstitials, the holes in the lattice that we discussed in the last section. And in fact, they fit best in those octahedral 6F holes, especially in a face-centered cubic iron lattice. And that actually gives rise to a lot of our heat-treatable steels and their awesome properties. So in the case of substitutional solid solutions, or solid alloys, solid solution alloys, as they're often called, not everything is going to want to dissolve in everything else. It's a little more complicated than in liquid solutions. So characteristics of atoms which will lead to good solid solubility is, first of all, same size, same atomic radius. You're going to want an atomic radius that's within 15% of one another to get good solid solubility. You're going to want similar electronegativities, which is usually very easily achieved with most of our structural metals because they're all typically first or second row transitionals and pretty similar because we're just filling up those D shells. It would be much more difficult, say, to dissolve something that's a semi-metal over on the right-hand side of the periodic table and say an alkaline earth or an alkali metal. Those would tend to probably form an ionic compound. The last is the valency of the solvent versus the valency of the solute. The solvent metal, the one that's in the majority in terms of the number of atoms per unit volume, you will get better solubility if that tends to have a lower valency than the solute. So one example of that is iron and chromium. Iron tends to want to be in the +2 or +3 valence state. Chromium tends to really be most stable in the +3. So you would tend by this rule to maybe get a little bit better solubility if you had chromium dissolving into iron than vice versa, because the +3 has the higher valency than the +2 solute to solvent. That is probably the least important driver. Definitely the big ones will be similar electronegativities and similar size. So if you look at copper and nickel and their sizes and their position in the periodic table, these are probably the most intersoluble of metals. That gives you a good example of the best of these solubility rules. And if you are looking for rules of solubility, these are called the Hume-Rothery rules, and they're just a general guide to solubility for substitutionals. Obviously for interstitials, you're going to get the best solubility when your solute atom is small compared to the solvent lattice. Okay, well obviously you can't dissolve things completely. Other than copper and nickel, you will eventually reach a limit where your solvent lattice doesn't want to accept any more solute atoms. Like I said, copper and nickel are really special that you can accept any amount. When you reach a solubility limit, you've gotten to the point where the material's energy can be lowered by rearranging atoms such that they segregate into another phase. So that phase will have its own composition. And this picture shows an example of that for a solid solution of, say, maybe copper and aluminum. If you imagine the orange circles being copper atoms and the gray circles being aluminum atoms, after a certain concentration of copper has been introduced, you have so much, the material reaches a point where it can dramatically reduce its energy if those copper and aluminum atoms rearrange to one little volume where they're in a 1-to-1 ratio. And that little phase is known as an intermetallic or a stoichiometric compound. They tend to be very hard, very strong. They tend to have properties that are quite similar to ceramics, and in fact share a lot in terms of bonding, even though they're metals. And so those will spontaneously nucleate under certain conditions of temperature and pressure. And again, that's in response to lowering the material's overall energy state, and it's a chemical drive more than a strain energy drive. So that's introducing a new concept in terms of energy, chemical energy driving material changes, not just interatomic position on that potential energy diagram. So the drive, the limits of solubility, and some of the drivers we'll see come from something more than just the strain energy relationship. So now we have two things driving material change, and I'll try to call them out. We will come back to the polymer defects at the end there. Moving ahead from 0D defects to 1D defects, linear defects, also known as dislocations. These are very important for forming processability and mechanical properties. They come in two flavors, one called edge dislocations, and that is literally just an extra half plane of atoms inserted into a crystal structure. Screw dislocations can be thought of as a spiral ramp resulting from shear deformation, and they work exactly the same way, except edge dislocations will move perpendicular to their own line, and screw dislocations move parallel. But other than that, they will each result in the same increment of deformation per unit movement and have the same stress or energy associated with moving them. Dislocations locally strain the lattice right at their end point where the ramp starts in the case of the screw dislocation, or where the jammed in plane edge ends in the case of edge dislocations. Just like the energy resulting, this is back to mechanical strain energy, that we had for vacancies or interstitial or substitutional solute point defects. The area around the edges of these linear defects, the surrounding atoms are not in the equilibrium positions, and so the energy of the crystal in that local area is a little bit higher, and that has the impact of reducing the stress required for plastic deformation quite significantly. So this is a cross-section diagram of an edge dislocation. You can see that at the top portion of this diagram, the schematic, there's right in the center, there's actually an extra plane of atoms, and it ends at the little T symbol in the middle of the diagram. And below it, the atoms are trying to actually move back into their equilibrium position. And if you think about this as being like having something stuck between your teeth, in the upper portion of the diagram, the atoms around that extra plane are in a state of compression, especially towards the very end of the plane. And then as you drop below the bottom end of that extra plane, the atoms surrounding right immediately below it are in tension. They're trying to move back in together. So you literally have two opposing strain fields at the end of this edge dislocation, the upper part being in compression and the lower part being in tension. Excuse me. So it would be analogous to, say, having a self-interstitial above and a vacancy below. So tension and compression. We quantify the increment of deformation of the material for increment of movement of a dislocation, both edge and screw, by something called a Berger's vector, and that's shown up on the top of the diagram. It's a vector direction indicating which direction the dislocation is moving and where the material is going to deform when it does move, and its magnitude will be dependent on the crystal structure of the material. This is related to the lattice parameter, and it also relates to the amount of strain energy that you have as a result of the dislocation, since that is actually changing the lattice parameter just a little bit. This is a diagram showing a screw dislocation. You can see it looks very different, but it results in the same kind of single increment of strain. You can see the spiral ramp in the 3D image schematic over on the left-hand side. The line coming out of the paper, out of the screen, it's perpendicular to the ramp, and the deformation index that you can see at point C, kind of towards the center of the slide, it shows where the ramp has indexed. So unlike the case of the edge dislocation where the Berger's vector is actually perpendicular to the line of the dislocation, this time it's parallel to it. But other than moving parallel to its own line, it works the exact same way as an edge dislocation with respect to a compressive and tensile strain field. and the energy of the crystal being raised right in the area, in this case, where the ramp begins, sort of where closer to A in the center of that left-hand side. Okay. I've mentioned several times the importance of dislocation with respect to deformation and plasticity and the way metals and all materials can plastically deform. So we're gonna go through two slides that help us envision that a little bit and put a few numbers on it, and we're gonna move back to our chemical bonding potential energy versus equilibrium spacing consideration again. So we're all back to elastic strain energy here. So we're going to take a crystal and we're going to try to deform it across a plane using shear forces. And you can see we're going to start over on the left-hand side, labeled initial state number 1. All of the atoms in the crystal are in their equilibrium positions with an R0 or R0 as being the equilibrium spacing. And we're going to push on it to the right on the top of the dotted plane and to the left on the bottom. So if you imagine this crystal coming out of the plane of the screen, we would have an area we're pushing on, so we would effectively have a stress on the top and the bottom, so we're applying a shear stress across that dotted plane. So initially, if we want to move it, the atoms are all going to index over such that they're now completely out of their equilibrium position. So if we were looking at their potential energy, we will have moved them up that right-hand sidewall of our potential energy well to a very high energy position where they're much further apart than they wanted to be. So, and if we looked at the energy associated with that movement, we would say, you know, we've moved from our equilibrium potential energy up a certain amount corresponding to how far off our equilibrium position we are. Then we'd multiply by the number of atoms to which that applies. Well, that's applied to every single atom associated with that shear plane along that dotted line. And you know, we're envisioning this crystal coming out of the plane of the screen and extending forever in both directions. That's a lot of atoms that we've just moved into a very high energy position. So assuming we can do that and nothing else happens, eventually we'll get to the point where they've all of those atoms move back into an equivalent low energy position in number 3 that's equivalent to where they started but indexed 1 over, because we're in a regular periodic array. We're in a crystal. So we have now achieved one R0 increment of strain that's shown at the top of that third schematic. Now the problem with this kind of process is, first of all, it requires a tremendous amount of shear stress. It would be impractical to come up with that much energy for ordinary material processing. In fact, you need something on the order of 20 to 150 gigapascals to achieve this for metals. And one of the things that limits is, even if we could come up with that much energy, it was cost and time effective in processing, it would actually be energetically easier to form a surface between the metal and the air in order to achieve that. That would happen at a lower energy, and that's called fracture. So it is actually energetically easier to break a material than deform it if we have to move each and every atom out of its equilibrium position through its highest energy state in that potential well, and then drop it back down at the next unit cell over. So in materials in which dislocations don't exist, like more perfect single crystals, or where they can't move easily, we often see materials fracturing without any kind of deformation, namely our ceramic materials and our other brittle materials. And so this is why. Now, if we have dislocations, on the other hand, we can restrict that kind of high energy movement to just around the edge of the dislocation. And that's the scenario we've set up here in this slide. So if you look at our two schematics, starting over on the left-hand side, we have a nice edge dislocation, and it's shown in the royal blue atoms, the extra plane of atoms. We're going to try to do the same thing. We're going to try to deform this material by applying some shear stress to the right above the dotted line or dotted plane effectively coming out of the screen and moving to the left on the lower part of that plane. But this time we don't have to move every atom. We only have to move the red atoms. And not only do we only have to move 6 atoms instead of a semi-infinite number, well, 6 in this cross-section. This is a plane going infinitely into the screen, remember. These are also already in a somewhat higher energy state. So we have 2 benefits going for us. We don't have to move as many atoms, period. We've changed it literally by 1 dimension. We don't have to move a plane of atoms, we only have to move a line of atoms. And second, they're already off of their equilibrium position because remember they're a bit closer together than they want to be with their compressive strain field up on the upper side of that plane and in tension below it because of the dislocation. So you have 2 advantages. So the right-hand side shows the relative positions that we get when we index that dislocation 1 Burger's vector or 1 unit cell over. We've achieved the same amount of deformation. We've still got R0 of net permanent plastic deformation. But to do it, we only had to exert about a half to 10 megapascals as opposed to 20 to 150 gigapascals, which we would have had to do to move the whole plane. That's 4 orders of magnitude or more less energy to get the same amount of movement. And again, it's coming from a double hit. We had to move fewer atoms out of their equilibrium positions, and because the dislocation preloaded those atoms that we did have to move with a bit of energy to begin with, the amount of energy necessary to move them through their most non-equilibrium point was less. This is most importantly for us who need ductility in materials. This is significantly less than the energy necessary to form a surface for fracture. So this means our stress to move and deform a material with a dislocation is less than the energy to fracture. So we can bend without breaking thanks to dislocations. So dislocations move much easier than a material that doesn't have them, but they do not move with equal ease on every crystallographic plane. It is easiest to move a dislocation, be it screw or edge, on a plane that is close packed and in a direction that is close packed. So dislocations will move easiest on our close packed planes in our close packed crystallographic systems, which is the 1000 and hexagonal close packed, and in fact that's the only plane in the hexagonal close packed system that they'll move on. And they'll move easiest on the 111 planes in face-centered cubic. Those are your close packed planes in those 2 systems. More importantly, they'll move easiest in the close packed directions, which is 111 direction in BCC and 110 family of directions in face-centered. If we had a single hexagonal close packed crystal, such as a zinc single crystal, and we started yanking on it in tension, we would get something that looks like the right-hand side of this schematic on the right on this slide, and the slip steps, which would actually be visible macroscopically on the sample, would literally correspond to those 100 close packed planes that we saw with the hexagonal close packed system in our crystallography discussion. So moving on to planar defects. These are 2-dimensional defects, planes and surfaces within a microstructure. There are, again, 3 different flavors, and as we go from stacking faults to grain boundaries, we are increasing crystallographic mismatch across the defect plane, and we are increasing energy. So a grain boundary is a higher energy 2D defect than a twin or a stacking fault. Stacking faults, and this is picking up at the bottom of this slide, it's when you have a stacking sequence error, and this is really specific to just our close packed systems, our hexagonal and face-centered cubic close packed. So if you remember, if you are building up in layers of close packed atoms per layer to make a face or face-centered cubic or hexagonal close packed crystal, If you're going to make, say, a face-centered cubic, you would have atoms in positions A, then B, then C as you stack up to get a close packed 3D structure. And you would have the AB sequence in hexagonal. So if you kind of intersperse those, if you had a couple of layers of AB in an otherwise ABC stacking sequence, then you would have what's called a hexagonal close packed stacking fault in a face-centered cubic structure. These are obviously planar because it's a whole plane, it's a whole stack, but it's very low energy. It's things are not too far off their equilibrium position, but they are enough that they can change mechanical properties a little bit. The next higher energy planar defect is called a twin boundary, and this is very important for deformation in certain materials on which dislocations cannot move easily, like the hexagonal system and certain types of brasses. And this is where you'll get another crystal form under the action of stress or sometimes thermal treatments that is effectively a mirror image of the other, and it reflects across a plane which is known as the twinning plane. So in this, the atoms are not, they're further out of their equilibrium position than a stacking fault, but nowhere to the extent that they would be in a full-up grain boundary. In a grain boundary, the crystal on one side of the boundary has no relationship to the crystal on the other side, other than they are the same crystal system and material. Their orientation is totally random relative to one another. And you get this by solidification or nucleation of a new crystal structure from an old one. The easiest way to envision this is the nucleation of a solid material in a liquid, where you'll start by, as you say, increase pressure, drop temperature. You'll nucleate new solid crystals in their parent melt. They'll grow in size, and each one of these is oriented in a completely different direction. And eventually they'll grow together and preserving that random orientation. And so the planes between them, and what you're looking at is a flat cross section, so the lines surrounding those grains are actually surfaces. So those are grain boundaries that you're seeing. They're very energetic defects because there's a lot more void space, and the angle between the different grains, the crystals, is random and sometimes is very extreme. This can form not just from a new solid phase nucleating in a melt. You will get the same kind of structure with a new crystal structure nucleating in another solid. So you could get the same exact kind of structure coming out of a new solid from an old solid. But it's the same exact process with respect to grain boundaries forming. So high and low angle grain boundaries. Even within grain boundaries, the highest energy of our 2D defects, some are higher than others. If you're looking now at a cross section on an atomic level of 3 grains, and the blue lines are showing your close packed directions within each grain, and the atoms are all touching in one grain, and then you move into the other grain and they're not touching, and that's because they're not oriented in the same direction. And so the higher the angle between those lines of close packed orientation, the higher the energy of the grain boundary between them. Along with being higher energy, because the atoms are on the average further off their equilibrium positions, we're talking mechanical strain energy, elastic, coming from that non-equilibrium position in the potential well. We also have a lot more physical void space. And so if we had to move something through the material, that would be the easiest place for it to move. So grain boundaries are places of high mobility and also high reactivity. So generally the rule of thumb is if anything has to move in a material, it'll move through the grain boundaries first rather than the center of the grain. And if anything's going to happen in a material, it will happen first at the grain boundaries. Just a rule of thumb. Note about processing and crystallographic orientation. If we don't mechanically process a material and we've just formed it and it's isotropic, all the grains are randomly oriented every which way. Dislocations will, like we said, want to move first on close packed planes and in close packed directions. And in our starting material, those are oriented equally in just about every direction. Well, say we applied some shear stress and we deformed it and we moved those dislocations. They moved first on all of the close packed planes and in the close packed directions of all the crystals that were conveniently lined up relative to the stress that we applied. And then they piled up and reached the limit of what they could move and activated other directions. And in so doing, the deformation was preferential in the directions of easiest movement. So we actually changed the material by moving those dislocations and ended up orienting the directions of easier movement of the crystal structure in line with the direction of deformation. So we went from having an isotropic structure to an anisotropic structure, much more similar to what you would get in a fiber composite, simply by relying on our dislocations, our 1D defects, to achieve plastic deformation in the material. So that's something very important to remember. Even if you're working with an isotropic monolithic material like some metal, the minute you start forming it, is not going to stay isotropic for long. So all of the properties will change, and if you're specifying yield or the need for additional ductility or even fracture toughness, it will be different in different directions after you form it until you recrystallize, and then you can reset. And we will talk about that in Chapter 8. So that is it for defects in materials. As you can see, we may call them defects, but they're definitely not defects the way you would think of in terms of quality engineering. They're actually essential features that we rely on for processing and for material properties, and are quite our friends as we look at forming and engineering materials. Next lecture we'll go into mass transport, where we'll take advantage of some of these vacancies and grain boundaries to move materials within others and look at the rates at which that would happen. We'll see you next time.